7 departments, and this is my country was compared to the European Union. My faculty has 8 engineering departments. We have the system of the integrated master's program. After 5 years, the students obtain the diploma engineer degree. That means bachelor and master together. And we are located in an olive tree field. And we have very old trees. This is something like 2,500 years. Our olive trees are considered as natural monuments, and we cannot take them out, and we have to maintain and keep them there. And this is a place where the philosopher Plato used to teach, and this is the reason our logo has his picture. And this was the row of our big philosophers. The first one was Socrates. The best student of him was Plato, the one we got his picture in our logo. The best student of him was Aristoteles. Aristoteles was really one of the most impressive ones because he has written a lot of books, and the most of them were not burned during the history. And he has also, he got a very good job. Left Athens and went to northern part, and he became the teacher of Alexander the Great. And after the teaching him, he got a lot of money, and he was practically independent, and he has worked harder for the philosophy and the physical sciences. And I don't know what he taught to him, but after his studies, he rode the horse and came to India. Anyway, Alexander, I mean. And his best student was Theophrastus. And Theophrastus worked a lot with Aristoteles, and since the previous ones have really worked hard on the philosophy as we mean it today, he has worked a lot on physical philosophy. That means he has written a lot of books about minerals, materials, plants, animals, and things like that. And when he was writing the book of botanology, some soldiers from the army of Alexander were coming back and bring him an information. He had no idea about that somewhere in India there is a plant that produces fibers, but he could not understand how it look like, and he has reported in his book about the plants that in India there is a tree producing wool. This was the fantasy he had about this. But this was the first information about cotton in Europe. And this is the reason you in Germany, you call it Baumwolle, because you got the information from his book. Baumwolle is the wool of the tree. And this was the first reference about the cotton in Europe. Imagine 3rd century BC, the first information. And finally, cotton came after 15 centuries in Europe. In the medieval times, we had the first cotton through the Arabs. So this is the book of him about botanology and so on. And this was the phrase that in India there is a wool-producing tree. This was the only phrase that informed the Europeans about the cotton. As I told you, after maybe 15 centuries, we got the first cotton fabrics. So let's go back now to our subject. Electricity and textiles, they don't like each other, as you can understand, because the majority of our textile fibers are isolators, and the majority of our textile materials are polymers, and polymers maintain covalent bonds. That means no free electrons and no electricity, no conductivity, and so on. However, we like conductive textiles because they could help us to create electromagnetic shielding applications, to create heating applications, to transfer electrical current for many purposes, to use sensors and to transmit the signals and so on. The story with the conductive textile started in the decade of '60 as a top secret research program in the United States and the Soviet Union, mainly for aerospace applications. And they had the first conductive fibers in this period. How can we get conductive fibers? By adding conductive particles, carbon or nanomaterials and so on in the polymer. Of course, if we want to have high conductivity, then we destroy the character of the polymeric uniformity. That means we reduce the textile properties. So we try to find a balance between conductivity and textile properties. Or to deposit conductive materials on the surface of the fibers. Even galvanic methods are used, and we create a sieve on the surface of the fiber. And what we do is to pray not to bend the fibers a lot, so that there will be no cracks. Otherwise, by high bending activity, then we have cracks and we destroy the conductivity. To use intrinsically conductive polymers, that means polypyrrole and poly whatever, but they are really conductive. They are quasi-conductive. They are semiconductors practically. And finally, to use the metallic fibers, this is what we do today. We use practically metallic fibers to have the conductivity we wish. Anyway, what we can do with the conductive fibers, we practically can create wearable systems. This is our dream, you know, when I'm thinking about the future. What I always think is to create textile-based components, use textile materials themselves in order to create electrical components, resistors, capacitors, inductors, in order to create electrical circuits textile-based. Of course, all these things are presuppose that we will have a power source. Power source means, in our mind, either to plug the cable and to provide power, or to hold the battery. But use of battery means a lot of things: how to charge the battery, how to connect the battery, what is the care of the garment. It's an open discussion. Last but not least, we have the energy harvesting issue. Somehow, maybe we will use textile materials so that we can harvest energy. That means to convert the energy of the body of any kind into the electrical energy. So this is a nice picture from a Chinese paper. They indicate more or less the amount of energy provided by the human body. And you can see that the most promising parts of the body to provide energy is the leg and the arms. And of course, all these things are in very low scale. You see, if you use the body heat, you can expect to receive something like 5 watts maximum. If you use the arm, 60. And that means that you will get tired soon because you have to move your arm. Anyway, the overview of the methods to harvest the energy is either to use thermoelectric generator, or pyroelectric is something similar. Some very modern biofuel cell and hydrovoltaic cells. We harvest the chemical energy, sweat or water vapor produced, very low capacity. Piezoelectric nanogenerators and triboelectric nanogenerators are really more promising, and we will see something about that now. Our research interests are about thermoelectricity, piezoelectricity, triboelectricity, and we use Peltier elements to harvest energy, but you will see the negative issues. The operation of the Peltier element is based on the delta theta, on the difference of temperature of the one side compared to the other side. And so we put a Peltier element on the garment. That means that the inner temperature is the temperature of the body, and the outer temperature is the temperature of the ambience. And you see that since we approach, the ambient temperature approaches the temperature of the body, the efficiency of the generator drops. So this method is very good if we discuss about systems installed in the polar area, in the North Pole, in the Southern Pole, where the environment is very cold and the body is hot, so it's very efficient. In our climate, practically it does not work. The piezoelectricity, reported first in 1880. Practically we have it in polymers 100 years later, and in textiles we have it since 2010. You know the principle of piezoelectricity. I don't want to bother you with basic physics and chemical knowledge. Practically we destroy the balance of the electrical dipoles. And the problem in this research project is that there is no commercially available testing equipment, so we have to create our testing equipment in order to test the piezoelectric fibers. So we are happy, of course, because in the last years all this design and development of instruments became very easy because of the 3D printers. You can create any mechanical part very easy. In the past it was a nightmare, now it's really very easy. So we have created the testing equipment, and we have the generation of the power. Practically, we are in the range for one single fiber in the range of nanowatts. But if we consider that on a garment there are millions of fibers taking part, it means that we expect that for every motion we will have enough energy to operate some wearable systems. The point of interest is that there is a loss of the piezoelectric properties over the time. According to our experiments, it takes, let's say, a few months, 3-4 months, and then the fiber is not anymore piezoelectric. There is no piezoelectricity because the polymers by themselves, the polymer chains by themselves are try to go to their initial position, and we lose the piezoelectric property. That means we have to hold them again, to stress them again electrically, in order to be able to produce piezoelectric energy. This is the negative and critical issue. In triboelectricity, it has been reported for another reason, 500 BC, and in Meltus, a city there in today's Turkey. And what is the issue? The issue is to create structures that they can convert the mechanical energy into the electrical, to be small size, small weight, light, flexible, to harvest energy for low consumption, of course, devices, and practically to base our activities onto common textile products. Because if you see in the literature for the triboelectricity, the material engineers, the material specialists use some exotic materials, some special membranes and so, that they operate, of course, very well, but they cannot be used on a textile structure. So our interest is focused on the textile materials. Practically, we consider that we can use the active, let's say, surfaces close to our arm, so that we will gain the energy from the motion, from normal motion of the arm while walking. And we have chosen very common materials: cotton knitted fabric, wool knitted fabric, and as a reference fabric, this PTFE, which is really very active. We have created a testing jig in order to test the samples, simulating the motion of the arm. And finally, the result is really good. We have no aging, there is no change of the properties of the material. For every motion, we have enough voltage and current to operate our systems. And you see that just using cotton and wool, we have an output of 3, 4, 5 volts. That is enough to operate our electronics. Of course, the power is low. The power is proportional to the power we provide to the generator. That means that the current is low, but enough for small applications. And we accumulate this energy on capacitors to store the electric energy for later use. So this is an overview of our research on the triboelectric and piezoelectric generators. However, the more components we add on the garment, the more restrictions we impose. So we need to somewhere to locate the transmission lines, to locate the generators and so on. That means that we occupy certain positions, we use different materials, maybe it's a cotton fabric and then you have to add a woolen patch or something like that. Or these materials, these added materials, they reduce the comfort. Care restrictions, can it be washed altogether or you have to remove it or not? In general, we have design challenges. It's not easy to imagine that automatically you can add the triboelectric generator in the cabinet. You have to think twice and more. Now, let's pass to our main subject. What is the connection between composite materials and electricity? Practically, sometimes we dream about electrically conductive composite materials. Why? Because they provide EMI shielding, electromagnetic shielding. Maybe we can use some conductive paths to transmit signals through the composite material. And this is also a tricky point, the electrostatic discharge, because sometimes it's very important to be sure that we don't accumulate static electricity on the composite materials, especially in aerospace applications. Keep in mind that a very interesting composites application is this textile-based concrete reinforcement. This reinforcement of the concrete is an old story, but usually they try to obtain it by just using fibers or simple grids. Nowadays there is a trend, this is mainly developed in Germany, in Aachen and in Dresden. They use 3D fabrics, and the problem here for many years was that the cement itself could not penetrate into the structure of the fabric. So these products were developed when the material scientists provided low viscosity cement. So it's very like the water, and it penetrates through the fabric, through the fibers and the yarns, and it became possible to have this fantastic structure, replacing the iron steel, and it gives the opportunity to create structures, beams, plates for construction, extremely thin with very high performance. I believe that this is one of the composite materials application that's really, it will have a really very fast, very big market, because all the other applications, they have really very dedicated markets and applications. This one can expand the use of the composite materials in our everyday life. The main problem is that globally the civil engineers use some software packages to calculate the beams and the properties of the buildings, and they have to create libraries to be used by the civil engineers. If they do that, after that it will be really very booming, the use of the textile beton. The structural composites are very interesting. You know, in percentage of the composite materials increase. I think this indicates very good the fact that the composite materials became more and more trustful. Now, what is our point of view? What we would like to have is to be able to measure online on the real operation the formations, because maybe in turbulence the wind is undertaking that deformation that it could be fatal for the composite material. That means to monitor the structural health online, and this is not that easy. All of us are familiar with the laboratory tests where we really punish the composites by punching, by applying tensile forces and pressure and so on. And the online systems are known but under development. So the idea is to use optical fibers, and we use some laser beams in order to destroy the continuity of the, practically to create crates in optical fiber. We transmit wide spectrum light. Because of these incontinuities, a part of the light is scattered, and what comes back is a part of it, and depending on the deformation of the optical fiber, but not only deformation, for the change of the conditions, that means even the temperature change can be monitored, even the pressure change. We can measure really many parameters by using these fiber bracket grating sensors. And it's so safe, that means you just put an optical fiber, pre-processed, to create these grates, and by observing the spectrum coming out, you can get fantastic information. So it's highly sensitive. We have used it to measure we have embedded an optical fiber in a shock, and we used it in order to see how to monitor the swelling of the leg during the flights, to see how it swells and comes back. Imagine how sensitive it is. It's very fast. It's light operating, though no electromagnetic interference. You can have on one fiber many positions to measure. That means there is not necessary to have 10 optical fibers for 10 measuring positions. And the design is very flexible. Everything is extremely good. We use it. We started the development of these systems in cooperation with our aerospace industry. They like to monitor the deformations of the composite parts in the airplanes. What we need to have is to have the graded optical fiber. First, we have to create the optical fiber. We take the virgin optical fiber, and then using the laser, we create the grades. optical spectrum analyzer and interrogator. And this is our point, our difficult point, because you have to have an instrument that is quite expensive and not that small, but of course is very precise. Then we have to find a way to embed the optical fiber into the textile composite material. These are the critical points. And this is our research activity. We try to design a small, reliable, cheap interrogator for obtaining the information. You can see some examples from the literature. You have the composite material here, and the optical fibers come out from the mass of the composite materials. They are embedded in the resin. Or you can see that you can embed the optical fibers into the multiple structures so that you can observe any deformation at any point of the composite shell. What is very interesting is that even the system easily can feel, sense, recognize the changes of the shape, the changes of the tension applied, but also the permanent deformations are recognized here. For example, in the aerospace industry, they are afraid always from the birds falling on the plane, and what will happen if you have in the nose of the plane, let's say 100 birds falling on it. They use these systems in order to see the permanent deformations. And you can see how the patterns change after 4 strikes, 25 strikes, 47 strikes, and so on. That means not only the transient phenomena, but the steady state can be recognized. And you can see microphotographs where the optical fiber is in the body of the composite material. Of course, practical problems, how we will connect the connectors to get this signal out. And you can see that the trials, how we used to put the optical fiber in the wing, for example, in order to get the information from the deformation phases of the operation of the airplane. And concluding, the electrical properties are an interesting research field for many applications, as we can see, mainly to harvest energy. And it's the textile structural composites shape a moving field for many advanced applications, and the combination of the actual measurement systems may increase the design and the development capabilities. And this is a nice embroidery from an island in Greece, and thank you for your attention.
Thank you. Thank you for inviting me. Morgan published to calculation and fractionation of colloidal particles dispersed in liquid. I am from Shinshu University in Japan. Shinshu University, located in here, almost center of Japan. Shinshu is nature-rich and surrounded by high mountains, so we can see the beautiful landscape all the season. In spring, cherry blossom. In summer, clear river. In autumn, red leaves. In winter, snow view. I don't recommend Shinshu in this season. It's terribly cold. But you like skiing, Shinshu is one of the best spots of skiing. I recommend. Shinshu University is famous for fiber and textile research field. So many distinguished professors, there are many distinguished professors about fiber. For example, Professor Emeritus Endo, he invented and created the carbon nanotube. So he is one of Nobel Prize candidates. And Professor Kim, he produced so many research results about electrospan nanofibers, nanofiber fabrication, functionalization, and many applications. He is the director of IFES, Institute of Fiber Engineering and Science in Shinshu University. I am deputy director, he is director, so he is our boss. So my specialty is also electrospan nanofibers. My research field is wet separation processes such as filtration, adsorption, oil-water separation, and so on. I am challenging to apply the nanofiber non-woven fabric to wet separation processes. For example, adsorption of solids. We prepare and functionalize the nanofiber non-woven fabric with various functional materials like this, and apply them to selective adsorption of some solids, heavy metal ions, and protein. Next, process of oil droplets. This is oiling water emulsion, in which very fine oil droplets in liquid. Inside this nanofiber coalescer, the small size oil droplets are collected by the fibers and form an oil film on the fiber surface. The oil droplets colloid and coalesce into a large size, and then the discharged large size oil droplets float and separate from the liquid. I think the nanofiber fabric is a very high performance coalescer. I'd like to explain these research results, but in next opportunity. Today, I will be talking about the most fundamental filtration of particles. Introduction. These same images are different types of filter media. This is nanofiber non-woven fabric, and these are some conventional microfiltration membrane. Both filter media are applicable to separation of fine particles. Conventional microfiltration membrane is recent frontier technology in water treatment, such as has such water treatment, wastewater treatment, recycling of water, and so on. On the other hand, nanofiber non-movable fabric is mainly applied to air treatment, such as this. Nanofiber fabric is not widely used in water treatment field because maybe the conventional microfiltration membrane is well established in water treatment field. As is clear from this photo, nanofiber non-movable fabric has a 3D network structure and high surface area and high porosity. So we can apply them to physical separation of suspended solid, chemical separation of dissolved matter, and high speed and high flow processing. However, its solid mix separation characteristics are poorly understood because few researches have been conducted. So, we focus on two particle separation technologies, filtration and wet purification. Filtration is the separation technology of particle and liquid, and classification is the separation technology of large particles and small particles. Both are the separation processes based on sieving function. I think nanofiber fabric is has good sieving function. First topic is application to filtration. At the previous conference, we discussed the comparison of the filtration performance between nanofiber non-movable fabric and typical microfiltration membrane. To summarize the basic performance, the distinctive feature of nanofiber non-movable fabric is to be significantly thin and porous. The nanofiber non-movable fabric has pore and particle retention performance equivalent to microfiltration membrane. Water permeation rate is several times higher than that of microfiltration membrane with the same pore size. In this study, we prepare the nanofiber non-movable fabric made of nylon 6 by electrospinning method in this way. The fiber diameter was variously adjusted by controlling nylon 6 solution concentration. The fiber diameter is in the range of 93 to 167 nanometer. And the fiber area weight onto base material was also variously adjusted like this. This is a schematic diagram of filtration test apparatus. We use non-dispersible polystyrene latex PSL with different particle diameter of 0.1, 0.143, 0.196 micrometer. Particle concentration is 2 ppm, and the filtration pressure is 50 kilopascal by applying nitrogen gas. The PSL suspension is filtered through filter media, and the PSL concentration in the filter was measured to evaluate the particle rejection R with this equation. Particle rejection R equal 1 means perfect rejection. R equal 0 means all particles penetrate. First result. This figure shows the pore diameter against the mean fiber diameter. As shown in this figure, the pore diameter is a range of 0.4 to 1.1 micrometer. This implies that separation performance is equal to microfiltration membrane. In addition, pore size is about 6 times larger than mean fiber diameter. Thus, pore size decreases with decrease in fiber diameter. This implies the separation performance can be improved by using thinner fibers. This figure shows the PSL particle rejection R against mean fiber diameter. As shown in this figure, the separation performance is improved by reduction in fiber diameter. Please note this part. Fiber diameter requires to retain 0.143 micrometer particles completely is about 125 nanometer. For 0.1 micrometer particles, fiber diameter required to retain completely is about 90 nanometers. So this implies that fiber diameter should be less than 0.9 times of particle diameter to retain them perfectly. This same image is the surface of nanofiber non-woven fabric fouled by PSL particles during filtration. The PSL particles smaller than pore size were trapped on fiber surface. Especially particles were retained on the surface of thinner fiber or in the interspace of thinner fiber rather than thicker fiber. This supports the previously mentioned result, in which the thinner fiber bring about high filtration performance. I'll summarize the results briefly. Pore size decreases and particle rejection increases with decreasing the fiber diameter. Its separation performance can be controlled according to purpose by adjusting the fiber diameter. More advanced separation can be attained by developing thinner fiber than ever. Okay, next topic is application to classification. It is of importance in widely diversified fields to uniformize the particle size of fine particles. So, wet classification by a porous membrane is one promising classification method because the large particles are captured particles and small particles pass through the membrane. However, the excessive deposition of larger particles on the membrane disturbs the passage of smaller particles. It is a critical problem. I think the nanofiber non-woven fabric is expected to be suitable for classification because a 3D network structure retains the larger particles completely, and high porosity makes the smaller particles penetrable. So, in this study, in order to evaluate the fundamental classification performance of fine particles through a nanofiber non-woven fabric, we conducted the fractionation experiments of binary mixture of large particles and small particles. We use a non-woven nanofiber fabric made of polyacryl nitride with mean fiber diameter about 400 nanometers. For reference, we use typical microfiltration membrane made of mixed cellulose ester. Their porosity and pore size as follows. This is a schematic diagram of fractionation test apparatus, which is substantially the same of filtration test apparatus. We use two types of cross-linked polymethyl methacrylate PMMA particles. Smaller particle diameter is 0.5 micrometer. The larger particle 1.0 micrometer size. To evaluate the fractionation performance, we use transmittance TP. Please note, it's not R. TP equal 1 minus R. We use the transmittance plotted against filtration volume. This prior to the fractionation test, we conducted the filtration of single component system of small particle or large particle. Small particle is almost all passing through both membranes. On the other hand, large particles were completely captured by both filter media. It's single component, not binary system. We hope to attain the same result also in binary mixture system. This is a result of the fractionation of binary mixture system of small and large particles. Large particles were completely rejected by both filter media. On the other hand, the nanofiber non-woven fabric has higher transmittance of small particles than typical microfiltration membrane, especially at alkaline condition, pH 11. This result is attributed to the difference in mechanism between two types of filter media. In the microfiltration membrane, a large particle layer on the membrane disturbs the passage of small particles. In the nanofiber non-woven fabric, a 3D structure and high porosity support the high fractionation efficiency. Also, from the same images, we understand this mechanism. I get back previous figure. Please note the effect of pH, only pH. The transmittance of small particles at 5.5 decreases rapidly, but that at pH 11 keeps almost 1. It means complete fractionation. We attained complete fractionation. This result can be explained based on the zeta potential. Nanofiber fabric and two PMMA particles all negatively charged. At pH 5.5 here, the repulsive forces among the particles and between particle and fabric are not so long. So large particles are captured on the surface of fabric and disturb the passage of small particles. On the other hand, at pH 11 here, the repulsive forces among particles and between particle and fabric are larger. And consequently, large particles are captured on the inside of fabric and do not disturb the passage of small particles. I'll summarize the result briefly. The nanofiber non-woven fabric has higher fractionation performance than the conventional microfiltration membrane. and is suitable for wet classification of fine particles. To keep high classification performance, it is important to adjust pH to the alkaline condition in which both particles and nanofiber non-movable fabric are more negatively charged. Okay, thank you very much for your kind attention, and sorry for my poor English speech.
For opening size of that fiber which you prepared, what is the opening of that membrane?
Opening?
Yeah, opening. Like in terms of pore volume, like that.
Opening, it means what size?
Means like any molecules you have, like previously you show like oil emulsion is going to be filtered from that medium. So my concern is what is opening of that non-fabric or that filter you prepared. So what is the opening size, like if you prepared like this, so what is the opening of that?
Spacing, distance.
Yes, it means pore size.
Yeah, pore size.
One micrometer, near 1 micrometer. It's small, large size of particles. Fine particles or oil droplet.
Okay. Have you checked the volume with respect to the time? In what time, how much volume it can be filtered? Yeah. If you take any solution and you are using your material, so at what time, how much volume it is going to be filtered? Can you check this in your study? Have you checked this one? You are getting my question? Okay, no problem.
Sorry, I'd like to explain later for you.
Okay.
Sorry.
Yeah, so please, we could conclude the discussion during the coffee and tea break.
Okay.
So thank you again.
Thank you so much.
Okay, this brings us to the final talk of the morning session. The speaker is our conference host, Professor Behera from TIT&S. Challenges and opportunities of textile composites. Okay, please.
Okay. Thank you, Professor Robert. I think the major portion of this conference is on structural composite as the theme of the conference. So, my presentation is a combination of many structures, or to give some idea how different textile structures can be used as preform to make structural composite. Before I proceed to my research part, let us have some idea what is the history of composite. Composite is nothing new. It was there for about 5,000 years ago. It's clear from this picture. From straw and mud bricks to aerospace applications. So the whole process or evolution has gone through this sequence. It was in the nature, then people started making polymer composites, sometimes during Second World War. To make this composite more stronger, we reinforce fibers and more predominantly textile fibers, maybe natural or synthetic. Then in between, two important processes were developed, filament winding and pultrusion. After that, people wanted to have very complex composite material using different textile structure. Our research basically is focused on this textile structure. That's why the theme of this conference was given, Textile Structural Composite. The word structural here means load bearing. A composite which can really sustain application of load, be it tensile, be it flexural, be it torsion, be it compression, impact, or any kind of load. Subsequently, as you have seen, yesterday Professor Robert lectured multifunctional composites. It is a kind of advanced textile structural composites. So the first question arises, why we develop different textile structure? The diagram is very clear. When we try to use different textile structures in the form of fiber, in the form of yarn, in the form of fabric, and more complex fabric. What those complex I will explain in my chapters. The properties change. So it's not only the properties, also applications, because depending on applications, we try to develop different complex textile structures. So the basic objective of developing advanced textile structural composite is, obviously we want to have a lightweight material. As I said, structural means it must be load bearing. As you have seen yesterday, Professor Robert lecture, you can develop different functionality. We call it multifunctional composites. And they are all advanced materials. I will tell you what is advanced materials in the next couple of slides. So based on this basic information, my presentation will go through this sequence. Let me give some idea about global composite industry. We have already given some information during inaugural session through the minister here. This composite material has a huge potential. Almost in every part of the world, the market is expected to rise in double-digit CAGR in India, although the global average is less. And as I said, we try to develop this material from textile fiber through structure, through composite, and we try to develop end product. Why I am showing end product? The market size which is mentioned here for the composite material, but not the composite product. The figure which is mentioned here, that is composite industry, but you know composite is an intermediate material. It's not the end product. These materials are used for different applications where the value addition is huge. So in terms of net market, the figure will be substantially higher. So what are the growth drivers for this market? We need more lightweight structures in aerospace, drone, defense and automotive industry, railway, marine, and so on. Another advantage where we want to substitute metal, so corrosion resistance is another attraction. In electrical resistivity and high flame retardant materials, structural materials for the machine components and in construction industry, and structural power composites. You have already seen yesterday power composites in Professor Robert lecture. So applications are, these are some of the major applications. if you look at the trend today, these are some of the emerging trends, and for which a lot of research is necessary to take forward this industry, particularly the low-cost carbon fiber. Why I am saying this? Today, if you look at the total composite industry, the 80% of the reinforcement fiber is glass fiber. Remaining 20% goes to other high-performance fiber and natural fiber. And as you know, carbon, which is one of the high-performance fiber and can be used for many applications, is expensive. So, a lot of research is being carried out how to produce low-cost carbon fiber. Also, people want to improve the glass fiber. And the third point, which is most interesting from manufacturing point of view, as you know, we are making composite using some reinforcement and resin. Resin takes its own time for curing. That slows down the manufacturing process. So, people are trying to develop a rapid cure resin system so that the pace of manufacturing can be improved, increased, so that cost of production can be reduced. And another trend is additive manufacturing, that's 3D printing. I will give you some information in my subsequent slides. And last but not the least, multifunctional materials, as I said. We try to introduce several other functionality to the composite material apart from its load-bearing capacity. Then second point is advanced textile structure. Let us first understand what is advanced materials. Advanced materials could be biomaterials, nano-engineered materials, auxetic materials, 4D materials, smart materials. These are some of the advanced materials available today all over the world. So what is advanced textile structure then? Maybe a plain woven fabric which you wear, or a single layer woven structure, or knitted structure, or non-woven structure is a very simple fabric. But what are advanced textile structures? Can you make a multi-layer fabric? Can you make a hollow fabric, spacer fabric, honeycomb structures, auxetic structures, or maybe profile structures, maybe radon structures? If you want to see these kind of structures, how they are manufactured, actual samples have been displayed in one of the stalls. You can have a look to this. And these are the structures developed, and already prototypes have been developed and characterized. So I will not go to detail how they are manufactured, because basic purpose of my presentation is to just show you what are different possibilities to make different complex textile structures which can be used as a preform to make complex advanced textile structural composites. If you look at the very first one, multi-layer fabric, which is a 3D fabric. So obviously, when it will be converted to composite material, it is thick, load-bearing. The specialty of this structure is delamination. So if you go for stitching of different layers, and when that structure will be subjected to any impact, they get delaminated. But if you make using these integrated 3D multi-layer structures, you can prevent those delamination. That is the best purpose. And obviously, last is impact energy. So what is the challenge then in this? Today, in this particular field, the challenge is machinery. Even as of today, there is no really popular commercial 3D weaving machine anywhere in the world. Although we have developed some of the prototype lab model 3D weaving machines in which we have developed all those complex structures, but they are not really commercialized to start commercial production in mass scale. So some of the companies, Donier, Optima, they have developed some machine, but really commercially they are not successful, not because the technology is poor, only because the cost is very high. My next structure is honeycomb structures. We call it 3D woven honeycomb structures. So what is honeycomb? We all know what is honeycomb. Look at the fabric and composite made out of it. We try to play with basic structure of honeycomb. It's a hexagonal structure. So not necessarily the unit cell of honeycomb could be hexagon. It could be pentagon, it could be triangular, it could be rectangle shape, it could be square shape, any shape. But we have to play with the parameters which is mentioned here. Opening angle, bonded wall length, free wall length, bond wall thickness, free wall thickness, and height of the cell. All these parameters, those are called construction parameters, attribute to the final property of the honeycomb composite material. And you can see all those structures can be converted to their respective composite material, and when we try to characterize them, it opens up many ideas how to optimize the construction parameter of these structures. Just I will give you one example. Look at this load deformation characteristic curve of these honeycomb structures. The special zone at the center of this curve is plateau region. We try to play with all those 6 parameters to enhance the length of this plateau region, because the energy absorption of this whole structure depends on this plateau region. Longer is the plateau region, higher is the energy absorption capacity. That's the basic fundamental to develop this structure, and we try to play with these structures in weaving so that you can develop high impact resistance structural composite material. These composites are also used for flexural properties. And look at this flexural curve, which is divided into 3 distinct parts: pre-buckling stage, post-buckling stage, and beyond the point B is failure occurs. Exactly in the similar manner, you play with these 6 parameters of its construction, you can enhance the zone up to A, between pre-buckling stage occurs. Higher is this point, more is flexural rigidity. That is how these structure parameters are optimized to develop advanced textile structural composites for honeycomb. So coming to applications where these materials are used, you can see these are some of the applications where this material is used, primarily to make sandwich structure. The core of the sandwich structure is a honeycomb material. So obvious point is, what is the challenge in this? Challenge is, there are 2 challenges. Weaving of honeycomb fabric itself on the loom, not that easy. Honeycomb cells can be created both in warp direction as well as wave direction. And the second challenge is how to convert this cellular structure fabric to composite material. A basic process is shown here. We first make these blocks. The blocks are inserted in the hollow space. Then it is kept in VRTM machine for resin infusion. And after that, when you try to remove these blocks from this fabric, it's a very difficult process. Not easy to remove them. During removal of these blocks, there is a probability that the structure may get damaged. So to make this composite material, a lot of skill is required to develop these honeycomb structural composites. My next example is profile structures. Look at what is a profile structure. Particularly, these structures are used for machine components. One example of machine components is, the primary definition of profile composite is, we have components in 2 different planes. It could be 3 different planes. So example here says 2 different planes or 3 different planes, vertical and horizontal. There is n number of alternatives to produce these structures. I will show you only some of the examples here, which are actual fabric produced and converted to composite materials of any shape. I will give you only one example of this. Let us this T shape. Look how this profile composite is substituting a T shape metallic. So what is speciality of this structure? The first speciality, obviously, since it is a fiber reinforced composite, it is lightweight. The second important property is junction strength. Look at where the material of two planes are bolted. If it is bolted, it creates a weak junction. But if it can be a single integrated structure, this junction strength is higher. That is what we have tried to prove. Look at a material with stitched junction strength, a material with integrated junction. And if you try to compare the junction strength properties of two different structures, obviously the integrated one gives higher than the stitched one. Next question arises, what is challenges in this research? The challenge is, look at the open structural diagram. Look at the junction point. The peak density at the junction point where the structure bends reduces. Means the presence of or the volume of fibers at the junction point is always lower than the volume of the fibers in the remaining parts. And textile structural composite strength purely depends on fiber volume fraction. Since at the junction point fiber volume fraction reduces, the strength is low. So challenge is, can you develop weaving process where the fiber volume fraction at the junction point can be maintained or very close to the remaining part of this section? That is what the challenge in this product. Next is obstetric textile structure. Obstetric fabric can be produced by weaving both 2D as well as 3D. So what is obstetric? We all know the material which gives negative Poisson's ratio. We have many natural negative Poisson's ratio material exist in nature. So what is negative Poisson's ratio is? If you apply a load in a structure in one direction, it also expands in transverse direction. And if you calculate the Poisson's ratio, which is ratio of lateral strain to longitudinal strain, you get a negative value. That's what the obstetric structure. There are n number of possibilities to develop obstetric geometry which can be converted to woven construction. Few examples are shown here, and it can be mathematically proved how this geometry gives obstetricity, means negative Poisson's ratio. Just take one example, which is a rotating square, and in this rotating square, if you try to apply load in any direction, horizontal or vertical, then the change in structure takes place as shown here in this diagram. If I take only unit cell of this whole structure and try to calculate its stress strain using very simple trigonometric equation, what is the value of x before stress, what is the value of x and y after stress, and find out stress strain, because initial dimension, final dimension difference, find out the strain, take the ratio of lateral strain to longitudinal strain, you will find the Poisson's ratio is negative. This is just one structure. Remember, thousands of such geometries are available or can be made. In nature, such geometry exists, and if you want to develop such geometry, you can also develop some geometry. In our research lab, we have also developed some new geometries which are patented, and they produce auxiliary fabric. And when you try to convert this auxiliary fabric to composite, the composite also shows authenticity. Using these principles, several auxiliary fabrics are made, and they are characterized. This plot shows lateral strain versus Poisson's ratio. Look at the curve coming down, showing negative Poisson's ratio. A very simple technique to calculate Poisson's ratio is take the fabric or take the composite, put 4 points, 2 points horizontally, 2 points vertical, apply the load, look at the change of position of these 4 points, from where you can get lateral strain over longitudinal strain, find out what is the Poisson's ratio. You will find if it is coming negative, the structure is auxiliary. I will show you just one example. So this is auxiliary fabric converted to composites, tested for Poisson's ratio. So obviously, question arises, what is the cause of auxiliarity in the structure? What is there in the structure which is giving negative Poisson's ratio? It's primarily, if it is a woven structure, due to differential shrinkage. When we make a woven structure, we can play with weave design. Change of weave design means change of float length. Change of float length means change of binding point. In weaving, we do simply interlacement. So interlacement of warp and weft creates a binding point. You go on changing the float length, go on changing the binding point, you will get differential shrinkage, and when the material is produced, tested, it gives you authenticity. So question arises, what these material properties? What special properties these material give? Many extraordinary properties you can obtain from these auxiliary structures. It gives high energy absorption, high shear stiffness, indentation resistance, synclastic behavior, variable permeability for which smart filter fabrics are produced using this structure, and high fracture toughness. There are many other applications of this. Because of these properties, these structures are used for many applications, particularly in defense. If the defense clothing used by soldiers can be made of auxiliary fabric, a lot of injuries you can prevent. And you can see blast resistance vehicles. We are using it for helmets. I am not giving another example in this context also. You can combine auxiliarity with honeycomb. We call it auxiliary honeycomb. You can get two properties combined together, auxiliarity as well as honeycomb energy absorption behavior. So these are some of the applications. Then obvious question arises, what is challenges there? The challenge is, what is the exact value of auxiliarity? For different applications, we need different negative Poisson's ratio. Is it possible to make reverse engineering? If I want my negative Poisson's ratio is minus 0.6, what should be the fabric construction parameters to give you that minus 0.6 negative Poisson's ratio? That is what the challenge and the research is necessary. The second challenge is when these structures are converted to composite by impregnating resins inside, we said the objectivity comes because of the differential shrinkage. Differential shrinkage is monitored due to change in distance between floating points. When resin is impregnated with the structures, every point is a binding point. The flexibility of the structure is reduced. So obviously the resin, common resin rather, used to make these auxetic composites are not the resin for auxetic composites. We need special resin. There are some resins are available now in the market. If those resins can be used, remember when we are making auxetic composite material using auxetic resin, we have a two-phase monitoring. First phase at fabric stage, second phase as composite phase, and third phase in between the selection of resin. Selecting right kind of resin, impregnating through the fabric, make a auxetic composite using auxetic woven structure is a hard task. That is what the challenge here. Next, coming to textile structural power composite. It's time? Okay. I have, because there are several, that's why I said I could complete only few things. So I can skip this. Textile structural power composite, Professor Robert, you have seen yesterday his lecture. We have also done some basic work. The point is, when we try to make functional composite, the functional composite functionality can be improved in two ways. One is structural function, another is non-structural function. So structural function, all I have discussed so far. Non-structural function is, for example, energy storage. One example is given by Professor Robert yesterday, supercapacitor. We have also done this exercise, supercapacitor, going to straight that material. We developed this composite material using carbon-carbon as electrode, both top and bottom, and glass fabric at the center, which acts as insulator, and make a composite. We try to characterize this. We get very low capacitance value. We try to functionalize the surface by giving some zinc nanorods treatment and get enhanced properties. We try to characterize these composites through electrochemical characterization. That's called cyclic voltammetric test. So you can understand how much energy it can store. Although, so far, the research conducted is not giving that high. You know, yesterday Professor Robert showed it is used for drone. Maybe drone needs a very small power, lightweight. Can it be used aircraft? Can it be used electric vehicle? You need large power. So you have to think how to have high energy storage. So there are some challenges in this. I think I should close because I must respect the timing. I had only two things to say. Additive manufacturing. And these are some three popular 3D printing techniques all over the world. That is SLA, SLS, and FDM. In all these techniques, the main constraint is these 3D printers use their own cartridge. You can buy a 3D printer with maybe only 1 lakh rupees. When you try to produce your product, you have to buy the cartridge of the same company. It's expensive. So we have developed our own 3D printing where you can produce textile continuous fiber reinforced composite, that too in thermoset. So this is our own model. The machine is already patented and commercialized. 3D printers, additive manufactured composites can be used for many applications. Modeling part also I am skipping, coming to conclusion. As I said, composite is basically lightweight engineering. So lightweighting is the wave of the future. We want carbon-free environment. Everybody is talking about sustainability. This is an approach towards sustainability. The major growth drivers of this area is transportation sector, growing demand of wind energy, construction industry, and auxiliary composite, particularly for defense applications. There are several challenges before us. Producing high performance fiber, as I said, to reduce cost of production. You need a lot of mathematical modeling to develop customized structure. Cost reduction in 3D fabric weaving because we don't have mass scale product producing 3D machine, and processing scale. Composite is not just only science and research, it needs good amount of skill to produce or convert these preform to composites. Thank you.
Coffee break now. Next session starts at 11. 11 for then the split sessions. Please be back. Oh yeah. Somebody's. Wait, you do.
Sanjay sir. Yes. Okay, sir.
Alright. Next one.
Sanjay sir. Okay, sir.
One more?
One. Fine. Okay.
Okay. And finally, that's what they have.
Okay. So it's certificate signed by me.
Thank you, sir.
Alright. Session is closed. Thank you.
Going on in Central Auditorium in lecture hall 1 and 2. So as per your expertise area, you can join any of these. The sessions will be starting